very good chapter in the physics whose name is motion in a plane. That is actually chapter number 4 from the 11th science physics part 1, chapter number 4, name is motion in a plane. Let's start with some fundamental concept. As you all know, you already studied in standard 10th, physical quantity. There are lots of physical quantities in physics. Few of them are scalar quantity and few of them are vector physical quantity. Let's recall the meaning about scalar and vector physical quantity. Scalar and vector. So first of all, let's understand scalar quantity means what? A physical quantity which required only magnitude for the description. For example, if anyone asks you what's a time, and if we replied okay, it's a 10 o'clock, 4 o'clock, 5 o'clock, no one can say like that 10 o'clock in the north direction, 10 o'clock in the south direction, because time is a physical quantity which required only magnitude, either 10 o'clock, 5 o'clock, 4 o'clock. Direction is not involved with that physical quantity. So a physical quantity which required only magnitude, scalar quantity required only magnitude is known as a scalar quantity. On the other side, vector physical quantity means a physical quantity which required both magnitude as well as direction. For example, if imagine a book or a block or something is lying on the table, and if anyone push that block, means applied the force on it. So you can ask two questions, that how much force act on it and in which direction. It means how much means magnitude is also involved and in which direction is also involved. So few physical quantity in physics are such that which required both magnitude as well as direction for the description. That physical quantities are known as a vector physical quantity. So vector physical quantity required both magnitude and direction. Let's write few examples of scalar quantity. First of all, there are lots of scalar physical quantity, but few of them are time, mass, density, volume, temperature are the physical quantity, etc. Lots of physical quantity which are known as a scalar one, but few of them time, mass, density, volume, temperature, one more path length. So these are the physical quantity which required only magnitude for the description. On the other side, vector physical quantity, we can give lots of example, but few of them: displacement, velocity, acceleration, force are the physical quantity generally known as a vector physical quantity. So one thing that I want to mention, that our chapter name is motion in a plane, and this entire chapter is actually based on magnitude as well as direction, means this entire chapter is based on vector physical quantities. Now as per name, motion in a plane. Plane means xy plane. We know that direction wise we have three dimension: x axis, y axis and z axis. So plane means either xy plane or xz plane or yz plane. Let's understand that what is actually the meaning of motion in a plane. Let me explain with the help of one example. For example, suppose this is x axis and this is y axis. Again, suppose this is x axis and this is y axis. Now there are two diagrams right now on the board. Let's understand that what is the meaning of motion in a one dimension and a motion in a two dimension. For example, if any particle, okay, any object performs the motion on this line, look at that line is a straight one, no doubt. Here also look at that, suppose one particle performs the motion on this path, on this line. So in both diagram, line is a straight one. If anyone asks you that in both diagram particle performs one dimensional motion ke two dimensional motion, so let's figure out it. Here the first diagram, during the motion you can see very clearly, during the motion only x coordinate will definitely change, but during the motion its y coordinate is remains as it is. It means that during the motion only one coordinate, x coordinate will change. So in the first diagram we can say that particle performs one dimensional motion because of its only x coordinate will change, y coordinate is as it is. On the other side, in the second diagram, during the motion when particle is here, its x coordinate and y coordinate is suppose 1 1. After some time particle is here, to see that its x coordinate is changed as well as y coordinate is also changed. So in this straight line during the motion, x coordinate as well as y coordinate, both coordinate will change. So in the second diagram specially we can say that particle performs two dimensional motion. In the first diagram particle performs one dimensional motion. So this chapter, motion in a plane, motion in a plane means either xy plane or yz plane or xz plane, whatever, it's a chapter of two dimensional motion. For example, I'll give you another example of two dimensional motion. Suppose if you have a something in your hand like stone or a ball, and if you throw that ball or a stone from your hand, so it performs generally this type of motion. Initially it goes high, reach at certain maximum height, then finally it has to be fall down due to gravity. So see that here we can see that here particle performs motion. How can we say that it's a one dimensional motion, ke two dimensional motion, ke three dimensional motion? Definitely we can check through the coordinate. During the motion its x coordinate will change as well as during the motion its y coordinate will also change. So it's a case of two dimensional motion, motion in a plane. So as I said earlier that this entire chapter is related to vector physical quantity. So one or two rules that I want to tell you. If any physical quantity is a vector, listen very carefully dear student, if any physical quantity is a vector physical quantity, rule number 1, you have to put an arrow above the symbol. For example, we know that velocity is a vector physical quantity. Generally velocity is denoted by V, symbol is V, but since it's a vector physical quantity, so you have to put an arrow above the symbol. Why we put an arrow above the symbol? Just to mention that this physical quantity required both. It required magnitude as well as arrow represents that this physical quantity required direction also. For example, acceleration generally is denoted by A. It's a vector quantity. You have to put an arrow above the symbol. Force is a vector physical quantity. You have to put an arrow above the symbol. Displacement is a vector physical quantity denoted by D. You have to put an arrow above the symbol. So this is the rule number 1. If any physical quantity is a vector one, so you have to put an arrow above the symbol just to represent that this physical quantity required magnitude as well as direction. Now generally arrow, here we discussed about the arrow. Arrow has two parts. This part is known as a head of the vector and this part is known as a tail of the vector. So many times we represent our hand to represent something, that look at the fan, look at the board, look at the board, look at the chapter number. So many times we use our hand to represent something. So in that case, this hand actually represents the position of that particle. We can consider it's in a vector where this part is known as the head of the vector, this part is known as the tail of the vector. So this arrow actually represents the direction. Definitely we use this arrow in this entire chapter. So overall this chapter is related to vector physical quantity. Let's move forward in a deep way in this chapter. Let's move forward. Let's start one very good topic of this chapter. So dear student, as I said earlier that chapter number 4, motion in a plane, entire chapter is based on vector quantity. So before move forward in the chapter, let's understand one more fundamental concept. Let's understand there are how many types of vectors are there available. Types of vectors. So number 1, first one, type of vector number 1 same vector, okay, let's understand with the help of one example. Just imagine that this is a table and one object is lying on it. Consider or also assume that 10 Newton amount of force act on that object towards your right hand side, and another 10 Newton amount of force act on the same object again towards your right hand side. So here in this diagram there are actually two forces are act. Both forces are same in magnitude, 10 Newton, 10 Newton, and both forces are same in direction. So if two vectors, as we know that force is a vector physical quantity, if two vectors are same in magnitude as well as same in direction, they are known as a same vector. Another example, for example, consider this is a road and also imagine that two vehicles, suppose this is a bus and this is a truck. So two vehicles are there on the road, both are moving. Suppose bus is moving in that direction, truck is also moving in this direction. Velocity, as we know, again velocity is a vector physical quantity. Suppose velocity of bus VB is 50 meter per second and velocity of truck is also 50 meter per second. See, so both vehicle, bus and truck, have same magnitude of velocity and direction wise also they are same in direction. So definition of same vector means if two vectors are equal in magnitude as well as equal in direction, they are known as a same vector. Remember, both should be equal, direction as well as magnitude. If both are equal, then they are known as a same vector. Last example, suppose this is vector A. Maybe this vector represents velocity, maybe this vector represents force. There are lots of physical quantity which are vector. One of them is vector A and this is vector B. So look at this last diagram, that vector A and B, see lengthwise, magnitude wise they are same in magnitude and they are same in direction. That's why we can write in this way, vector A is equals to vector B. Remember, in this entire chapter you can put equal sign only if two vectors are same in direction as well as same in magnitude, otherwise not. So this is the type number 1, same vector. Second number type of vectors, number 2, parallel vectors. Parallel vectors. Again example, before giving the example of parallel vector, look at this diagram. These two vectors of force are also known as a parallel vector. Another example, suppose imagine that this is a table, one object is lying on it. Suppose 10 Newton amount of force act towards your right hand side as well as another 2 Newton force also act towards your right hand side. Though they are not same in magnitude, but agar they are same in direction, if two vectors are same in direction, then they are known as a parallel vector. Direction, whether they are equal or not, direction wise it must be equal in direction. Magnitude wise they are equal in magnitude or not equal in magnitude, it doesn't make any difference. So remember, magnitude and direction both are equal, then they are known as a same vector. Agar only directions are equal, then they are known as a parallel vector. Type number 3, anti-parallel vector. Anti-parallel vector. Another example, assume that again this is a table, one object is lying on it. Suppose 10 Newton amount of force act towards your right hand side. Another, any, you can consider 10 also, you can consider 5, any other value. Look at this diagram. Here two forces are act on an object, but both forces are opposite in direction. So these are known as an anti-parallel vector of force. So definition of anti-parallel vector means if two vectors are opposite in direction, then they are known as an anti-parallel vector. And one more thing, that angle between anti-parallel vector is 180 degree. Because suppose one force act towards your x-axis, towards x direction, another force towards negative x direction. So angle between x direction and negative x direction is 180 degree. Two parallel vectors are same in direction, so angle between them 0 degree. Same vectors is same in direction, that's why angle between them is also 0 degree. But two anti-parallel vector, definition of anti-parallel vector means two vectors are opposite in direction, then they are known as anti-parallel vector. And last, type number 4, aparallel vector. Aparallel vectors. For example, again this is a table, one object is lying on it. Suppose 10 Newton force act towards your right hand side, another force acts somewhere in cross 5 Newton. See, angle between these two forces are not 0 degree, not 180 degree. Actually these two forces are not same in direction, not opposite in direction. It means that these two vectors of force are not parallel, not anti-parallel. So always remember, if two vectors are neither parallel nor anti-parallel, they are known as a parallel vector. Angle between two same vector is 0 degree. Angle between two parallel vector is also 0 degree. Angle between two anti-parallel vector is 180 degree. Whereas here angle between two vectors are not equals to 0 degree and as well as not equals to 180 degree. It means that they are not parallel, not anti-parallel, they are known as a parallel vector. So these are the types of vector will helps you in the fundamental concept to understand the next topic, dear student. So let's understand another topic. So dear student, just before some time we understand types of vector. Number 1 same vector, number 2 parallel, number 3 anti-parallel, number 4 aparallel vector. Again briefly, let's recall the definition of all 4 types of vectors. Same vector means magnitude as well as direction both are equal, then they are same vector. Only directions are equal, so they are parallel. Two vectors are opposite in direction, then they are known as anti-parallel. And if two vectors are neither parallel nor anti-parallel, are known as a parallel vector. Let's understand what is the meaning of position vector and displacement vector. Position vector and displacement vector. So meaning of these two words, let's understand with the help of one diagram. Dear student, let's consider this is y-axis and this is x-axis. So this is known as a xy plane. XY plane. Now randomly let's choose a path on which one particle is performing motion. So randomly, for the sake of simplicity, suppose this is the path on which one particle is traveling, performs the motion. And initially means suppose at time t is equals to 0, suppose particle is at A point. Start the motion from A point. So with respect to origin, suppose this is origin, it's our respective point. Look at this arrow. Actually this arrow represents the position. Just before some time I'll mention that so many times we use our hand to represent something like look at the fan, look at the ball, look at the tube light, etc. etc. So in the same way, this arrow actually represents the position of the particle with respect to origin. Head of the vector is at particle's position and tail of the vector is at origin. So it means that this arrow represents initial position of the particle. Let's call it R0. So here R0 is known as a initial position vector. represents the initial position. Now as I'll say that particle performs the motion on this path. So suppose after some time particle reach at B point, suppose at time t is equals to t, particle reach at B point. Again with respect to origin, I'll draw another arrow. To look at this, another arrow also represents position of the particle, but it represents actually final position. Let's call it R. So here R is known as a final position vector. So what is the actual meaning of position vector? So position vector means if a vector represents the position of any particle with respect to some reference point, here reference point is origin. So if any vector represents the position of any particle with respect to some reference point, so that vector is known as a position vector. Now dear student, this is initial position vector, this is final position vector. We would like to now know that displacement vector means what? A is the initial position, B is the final position, this is the path on which particle is travel. So a line joining between initial and final position. Look at this arrow, look at this red color vector. It represents actually the displacement vector. This is our displacement vector. Displacement vector generally is denoted by delta R, and always remember displacement means final position minus initial position. Final position vector is R minus initial position vector is R0. So this delta R represents the displacement vector, and also remember this is this black line, the curved one, is actually the path on which the particle is traveled. So this is known as the path length. Whatever the length of this line is known as a path length, and this is known as a displacement. For example, another let's understand the difference between path length and displacement. Difference between path length and displacement in a very quick way. For example, suppose let's consider a square. Particle is initially here at A point, then it goes from A to B, then it goes from B to C, then it comes from C to D. So a path on which the particle is travel is A to B to C to D, and consider that each side of the square is of length 5 meter, 5 meter, 5 meter and 5 meter. So what will be the total distance traveled by the particle? 5 plus 5 plus 5 plus 5. So it means that path length is 20 meter, and remember is a scalar quantity. Path length is a scalar quantity. Path length means total distance traveled by the particle. Now what will be the displacement in this example? Displacement. So this is the initial position and this is the final position. This is known as a displacement. Displacement is only 5 meter. The shortest distance between initial and final position is known as a displacement. So that is the difference between path length and displacement. Again, in this diagram you can see 3 vectors. 2 are position vector and red color is the displacement vector. So in a simple way, this diagram represents the meaning of position vector as well as displacement vectors.